Okay, so let's unpack this. I want you to imagine an assassin, but, I mean, get that Hollywood image right out of your head. There's no tuxedo, no silencer, no rooftop sniper nest. This assassin is invisible.
It's everywhere.
It's everywhere, and it's probably attacking the most expensive assets in your facility, like right this second.
And it's not a cyber attack.
Yeah.
It's not sabotage.
No, not at all.
No, it's much more mundane, which, makes it even more dangerous. It's moisture.
Just water.
It's plain old water vapor.
We're looking at a stack of research today that paints honestly, a terrifying picture of what happens inside industrial equipment. We're talking oil and gas rigs, massive utility transformers, heavy manufacturing plants.
Yep.
When you let the outside atmosphere get cozy with the inside of your machinery.
It's the silent killer of reliability. And what's so interesting about the sources we have today is that they argue the cure isn't some, multi-million-dollar digital overhaul.
No.
It's hardware. Specifically, this one device called a desiccant breather.
And we have the specs, we've got models from Air Sentry and Decase, we've got procurement strategies, and a lot of physics to get through. So what's the mission for this deep dive?
I think the mission is to shift the mindset from firefighting to foresight. We need to understand why our machines fail so we can stop, funding our own inefficiencies.
Funding our own inefficiencies. I like that. Okay, so let's start at the crime scene. Why is this happening? I think most people, and I include myself in this until I read this stuff, assume a big metal hydraulic reservoir or a gearbox is sealed.
You'd think so.
It's metal. It's bolted shut. It should be a bank vault.
It's definitely not a bank vault. It's a lung.
A lung.
A lung. These machines breathe, and they have to. It all comes down to basic thermodynamics.
Okay.
Think about a large hydraulic press running a shift. That oil isn't staying at room temperature, right? It heats up 130, 140 degrees Fahrenheit.
So friction, that generates heat.
Right. And when things heat up, they expand. So the oil expands, but more importantly, the air sitting in the headspace.
That little gap at the top.
Exactly. That gap between the oil level and the top of the tank, it expands rapidly. And that pressure has to go somewhere.
So it pushes out.
So the machine exhales air out through the vent port.
Okay, that makes sense. It's pushing air out. That seems harmless.
The exhale is harmless. The danger is the inhale.
Ah.
The shift ends or the load drops and that massive tank starts to cool down. The air inside contracts, the oil volume shrinks, and now you have a vacuum.
And nature hates a vacuum.
Hates a vacuum. So that tank just sucks in air from the outside to equalize the pressure.
And this is where it gets messy. It's not sucking in, clean, sterilized lab air.
Not at all. If you're in a coal plant, it's inhaling coal ash. If you're in a paper mill, it's inhaling steam and chemical vapors. If you're in a standard factory, it's just sucking in grit and humidity.
And the sources all emphasize that humidity is the real killer here. I want to drill down on this because water in oil sounds bad, but why is it catastrophic? Is it just that water doesn't lubricate?
It's so much more chemical than that. It's not just that they don't mix. When water gets into a lubricant, a process called hydrolysis kicks in. The water literally attacks the additive package in the oil.
The additives you pay a premium for. The anti-wear stuff.
Exactly. Things like ZDDP zinc, dialkyldiethyl phosphate.
Okay, yeah.
Water breaks them down.
Right.
So you're losing your anti-wear protection. But then the water promotes oxidation. It starts forming acids.
Acid.
So now your oil isn't just a poor lubricant. It's actually becoming corrosive. It starts eating the metal surfaces it's supposed to protect.
And the sources mention varnish, which sounds like something you'd put on a coffee table, but I gather it's not good inside a turbine.
It's a total nightmare.
Yeah.
Varnish is this sticky, sludge-like byproduct of that oxidation. It just coats everything.
Oh, wow.
It clogs valves, it gums up filters, and it acts as an insulator so the machine runs hotter, which just causes more oxidation. It's a death spiral.
And this all starts because the machine took one breath of humid air.
Precisely. And in transformers, the stakes are even higher. The insulation inside a transformer is basically paper.
Right.
If moisture gets into that paper, it degrades the dielectric strength. You end up with short circuits, tripped relays, or even an arc flash.
So we have the problem. The machine breathes, it inhales moisture, the oil turns to acid, and the machine dies. So enter the hero of our story, the desiccant breather.
The unsung hero.
On the surface, it just looks like a plastic canister you screw onto the top. But looking at the schematics for these Air Sentry and Decase models, there's a lot going on inside.
It's a multi-stage defense system.
Yeah.
I mean, think of it as a gas mask for your equipment.
Walk us through the anatomy. So air is being sucked in. What happens first?
First, it hits a particulate filter. This catches the big stuff, coal dust, fly ash, metal shavings floating around in the air. We're talking filtration down to 2 microns in some of these high-end models.
Wow, that's tiny.
It's finer than a human hair.
Okay, so the air is clean now, but it's still wet.
It's still wet.
All right, so next, it passes through the main chamber, which is filled with silica gel. This is a hygroscopic agent.
Meaning it loves water.
It aggressively bonds with water molecules. As the air passes through that bed of beads, the moisture is just stripped right out.
So by the time the air actually touches the headspace of the oil tank,
It's bone dry. We're talking nearly 0% relative humidity. You've stopped that chemical reaction before it could even start.
now this is where I want to get into the specific hardware, because the sources we have, specifically looking at the Air Sentry lineup, make a huge deal about check valves.
Yes, this is a crucial differentiation.
I was looking at the specs for the Air Sentry G12S2NG, which is a catchy name, by the way, and it lists a top and bottom check valve system. My first thought was, doesn't that restrict the airflow? You know, if you put a valve in the way, are you going to starve the machine?
That's a common fear, but the engineering here is really precise. These check valves have a very low cracking pressure, usually around like 0.1 psi.
So they open easily. They open almost instantly when the machine needs to breathe. But, and this is a real aha moment, they close the second the breathing stops.
Why does that matter?
Well, think about a standard breather without valves. It's just an open hole to the atmosphere.
Right.
So even if the machine is turned off for the weekend, that silica gel is just sitting there, exposed to the humid plant air. It's absorbing moisture 24/7.
So you're using up the life of the filter just to dry air that isn't even going into the machine?
Exactly. You're wasting money. The check valve acts as a gatekeeper. It says you can only come in if the machine needs you.
Okay.
This extends the life of the desiccant significantly. In really high humidity environments, like a paper mill or a plant on the Gulf Coast, a check valve breather might last 3 or 4 times longer than a standard open one.
So for that G12S2NG, that 2-inch connection and the check valves make it a real heavy hitter. The sources say this is for critical assets.
Right. You'd put this on a large hydraulic reservoir, a main turbine, a large storage tank. The 2-inch connection allows for that high airflow volume, so you don't risk creating a vacuum in the tank during a rapid cool down.
But you wouldn't put that beast on a little gearbox.
No, it's total overkill, and it probably wouldn't even fit. That's where you have something like the Air Sentry G5S1N.
The compact option.
Yeah, the compact one, 1-inch connection. It's designed for those tight spaces, maybe a small pump or a gearbox tucked away inside a conveyor system.
But it still has the same filtration.
Oh, absolutely. It's just right size for a lower airflow volume.
And then we have the Decase DC-4. The sources describe this one as the workhorse.
The DC-4 is legendary. It's the standard, rugged, general-purpose breather. It doesn't always have all the fancy check valve bells and whistles of the high-end Air Sentry units, but for general lubrication protection, it's just reliable, proven, incredibly effective.
The bread and butter.
It really is. It's the bread and butter of industrial protection.
This brings up a really interesting debate I saw in the maintenance notes. Cartridge versus bulk refill. Because looking at these lines, you can buy them as disposable units, you just screw them off, throw them away, or you can get refillable ones.
And this is a classic trade-off.
My first instinct is, well, go refillable. It has to be cheaper to buy a bucket of silica gel beads than a whole new plastic housing every single time. It seems greener, too.
And on paper, you're right. The bulk silica gel, especially that blue indicating gel mentioned in the text, is much cheaper per pound. For a massive transformer that holds, say, 50 pounds of desiccant, you absolutely want to refill. You're not going to swap a giant steel housing every month.
But there's a but coming. I can hear it.
There's a big but. Reliability is all about control. When you open a breather housing on the plant floor to pour in new beads, what else are you pouring in?
The atmosphere. The dust.
Exactly. You're opening the entire system. If you're standing in a coal-fired power plant and you pop the top of the breather, you might be dumping coal dust right into the center tube. Plus, it takes time. A technician might spend 20 minutes carefully refilling a breather.
Whereas a disposable cartridge
Takes 60 seconds. Unscrew the old one, screw on the new one. You never expose the clean side of the system to the dirty air. So if you're in a really dirty environment, or if your labor costs are high, disposable cartridges are often actually cheaper in the long run.
because they're safer and faster.
Much safer, much faster.
It's a nuance I totally miss. It's not just the cost of the beads, it's the cost of contamination risk.
Reliability is always about risk management. always.
Speaking of management, let's talk about the visual management aspect, because one of the coolest things about these devices, and I use cool loosely, we're talking about filters, is that they talk to you.
They do. The silica gel is color indicating.
It's like a mood ring for your oil.
Affectively, yes.
Yeah.
When the gel is dry and active, it's one color, usually gold or blue. As it absorbs water and becomes saturated, it changes. Gold turns to a dark green, blue turns to pink.
And this solves a huge problem for maintenance teams, doesn't it? Because usually to know if a filter is clogged, you need a gauge or you have to take it apart.
Right. With these, the text mentions a 60-second check. A technician can just walk down the line of pumps, just glancing at the breathers.
Gold.
Green, boom. You stop at the green one, write a work order. It turns maintenance from a guessing game into a simple visual process.
Management by walking around.
That's it. And that speed matters, because if you catch the saturation early, you swap the breather and no moisture gets into the oil. If you ignore it, well, then the breather becomes just a wet sponge sitting on top of your tank, which is actually worse than nothing.
Okay, let's pivot to the business case. We've covered the physics and the hardware, but if I'm listening to this and I need to convince my plant manager to spend money on high-end Air Sentry breathers with check valves instead of the cheap plastic caps we've used for 20 years, what's the argument?
The argument is ROI, specifically focused on what the sources call legacy costs.
Break that down for me.
We talked about oil earlier. Oil isn't cheap. But disposing of oil is incredibly expensive because of environmental regulations.
Sure.
The sources cite data showing that if you keep the oil dry and clean using these breathers, you can extend oil drain intervals by 200%, even 300%.
Wait, hold on. So instead of changing the oil every year, you change it every 3 years.
Or even longer. I've seen hydraulic systems run on the same oil for a decade because they kept it chemically pure. That savings alone, just buying 60% less oil over 10 years, pays for the breathers 100 times over.
And that's before we even talk about downtime.
Exactly. That utilities case study in the source material is powerful. They had moisture getting into transformers, and it was leading to week-long outages.
A week.
You have to take the transformer offline to dry out the insulation. That is lost revenue. That is angry customers.
And overtime pay for the crew, I'm sure.
Oh, yeah. By installing proper breathers, they stopped the ingress. They turned an emergency, which is chaotic and expensive, into a simple, scheduled maintenance task of just swapping a filter.
That's the shift from reactive to proactive.
That's it right there.
But there is a procurement trap here, right? We saw this in the notes about suppliers like PE Energy. If you have a massive plant, you might have 50 different kinds of assets. Pumps, gearboxes, transformers. If you buy a different breather for every single one,
You enter SKU hell.
SKU hell.
You have stock-keeping units for 50 different filters. You run out of the one you desperately need, but you have 10 of the ones you don't.
So the strategy is standardization.
Absolutely.
Yeah.
The expert advice here is to audit your facility. Find the commonalities. Maybe you can put the Decase DC-4 on 80% of your gearboxes. Maybe you standardize on the Air Sentry G12 for all your large hydraulic units.
Just reduce the variables.
Exactly. And then you work with a supplier, like a PE Energy, to bundle that procurement. Instead of buying one filter here and there, you buy for the whole year. You get consolidated invoicing, and most importantly, you manage lead times.
Lead times. That's the phrase that scares everyone these days.
It should. You do not want to be in a situation where a critical breather is saturated, the machine is unprotected, and your vendor says, oh, that's backordered for 6 weeks.
That's how you kill $1 million machine.
That's exactly how. Smart buyers are asking 4 questions. What are the pressure cycles? Is the indicator visible from the floor? Is it field replaceable? And can the vendor guarantee consistent media delivery?
Consistent media delivery, so you mean, do they actually have the silica gel in stock?
Correct.
Yeah.
If you rely on a bulk refill strategy, running out of gel is a disaster. You need a partner, not just a catalog.
You know, as we've been diving deeper into this, I'm realizing that this isn't really about breathers. It's about a whole philosophy of ownership.
That's a really profound way to put it. I think you're right.
Well, just think about it. If you allow moisture to enter your machine, you are accepting that the machine will degrade. You're accepting that the oil will turn to sludge. You are accepting that you will have to shut down for emergency repairs.
You are choosing to fail. It's a slow failure, but it's a choice.
And the alternative, installing a desiccant breather, is choosing reliability.
It's cheap insurance. A breather costs, what, a few $100s?
Yeah.
A gearbox rebuild costs $20,000. A transformer failure can cost millions. The math is just undeniably in favor of the breather.
I want to leave the listener with that thought about legacy costs we touched on, because I think a lot of people see maintenance as just a fixed cost. It costs X amount to run this factory.
But that's a fallacy.
Right. If you aren't upgrading to modern desiccant breathers, are you actually paying more money to maintain obsolete practices?
Yes, you're paying for the privilege of inefficiency. You are paying for the labor to change oil that shouldn't be dirty. You're paying for the bearings that failed 2 years early. You are funding the consequences of breathing bad air.
That is a painful check to write. Here's my payment for ignoring the problem.
It is. But the good news is, it's an easy fix. The technology works, the physics, the check valves, the adsorption. It's solid science. You just have to decide to use it.
So the call to action for everyone listening, go walk your plant floor. Look at your reservoirs. If you see a simple J-tube or just an open pipe, you're looking at an open wound.
And check the color on the ones you do have. If it's pink or green or whatever that saturation color is, change it.
Stop letting the assassin in the front door.
Keep it dry, keep it running.
Thanks for deep diving with us today on the silent science of reliability. We'll catch you on the next one.